3 is add the components together. Now you might be wondering, why do we add the components together? How does this make any sense on a graphical level? So I'm going to put some vectors, I'm going to put some arrows together to show you how it works. So let's go here, and I am going to use my select tool. So I'm going to select this resultant vector and copy and pasting it, or not. I've copied a few other things, that's fine. Okay, so there's my resultant vector in black. That's the one that I want. I'm gonna get rid of this red one actually. I don't think it's gonna like me. There you go. Because what I'm gonna do is, because that's my resultant vector, I'm gonna show you what happens after I add in all of my individual components onto this RT. So notice my RT starts over here. So I'm going to take this green arrow here. Oopsie, it's not what I want to do. I'm going to take this green arrow for S1X and see if I can copy and paste this guy back over here. Getting close, okay, and I'll fill in the rest of the blanks. I just want to make sure I have the right length here. So this is my S1X, okay, and now I'm gonna copy and paste my S2. So again, I'm gonna click on my S2X, copy and paste that one. So after putting this one together, I have put it right underneath my S1X, my horizontal component of my first vector. Now I'm putting down, this is S2X that I've put down here. And notice that when I add the two vectors from tip to tail, remember adding vectors is tip to tail. After I add the two vectors tip to tail, notice that my resultant vector from the initial point to the final point gives me exactly the x component of my resultant vector. So this guy over here, this red arrow vector, this is essentially x1x plus s2x. The reason why it's shorter is because S1 is in the opposite direction of S2, so there's some cancellation of the bit of that arrow to leave me with a smaller one. And mathematically, we're going to look at that why is it so later on. Okay, that one is for my horizontal component. Take a look at my Y components this time. I'm going to do the same thing, which I'm going to copy and paste all the lengths of my arrows. This is my S1Y. I'm going to try to see if I can match it onto my new drawing here. So there is my S1Y. Let me label this S1Y. And now I'm going to copy and paste my S2Y. Let's take this length of arrow here. I copy and paste, and then I put it, trying to align it tip to tail over here. And I think somehow, okay, maybe because notice that here it's not exactly aligned on the straight line here, so I might have to put it down a little bit. So let's readjust. Okay, I've slightly fixed this up a little bit, so that's my S1Y, and above here is my S2Y. Pardon the poor drawing and the realignment here. It looks a little funky. I wish I had better, if I could use some rulers, but anyhow, here it is. You get the idea. Notice that if I add my two vertical components of my two vectors, notice that it gives me the total vertical component of my resultant vector. So on a graphical scale, in this picture you can see how adding up the two components gives me that component in my resultant vector. So that's what I'm going to do. I'm going to start with my x's. I'm going to add my x components together, and this should give me the sum of the two individual components. So adding components. I'm going to start with my x components. Now, when I add these two components together, I need to pay attention to directionality. Directions matter. Okay, because why? Because if you take a look, one is opposing the other motion, which means if you walk back to where you started, you're not going to be displaced as far as you think you would be. So I'm going to start with S1. S1x plus S2x, and then including the negative sign, I have negative 3.276 dot dot dot, and I'm gonna add 7.713 meters dot dot dot. After I add the two, I believe these were A and B on my graphing calculator. A is supposed to be negative, so negative answer plus alpha B, and I should get 4.436. 4.436 dot 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 meters, and because it's now positive, and since positive is just towards the east, this is east. And I will save this as a x value for my x component of my triangle. So that's my x component after I add it up. For my y component, I'm going to add s1y plus s2y. And because these are both in the north direction, I don't have to worry about negative signs, luckily. This is 2.2943 with 9.19 dot 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 meters. And adding these two up, I'm going to add alpha C, and alpha D were the two numbers that I stored on my graphing calculator. 11.486. 486 dot dot dot, and this is north because both of the vectors point north. When they add up together, I will store this as the y component of my graphing calculator. Okay, so we can even write some of these in. So the y is 11.4 dot 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 meters. In my horizontal displacement is 4.4 dot 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 meters. So I have now the two components of my resultant vector. So now I can calculate my resultant vector finally, at least for the magnitude. Let's start with RT. This is equal to, using Pythagoras, the square root of my total y, which is 11.48 dot 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 squared meters, this is meter squared, plus my horizontal, which is my 44.4 dot 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 meters squared. I take the square root of the sum of these two squares. And on my graphing calculator, this is alpha x squared plus alpha y squared. I take the square root, and this gives me 12.31. 12.31 is going to round to two significant figures, so I'm going to leave it as 12 meters. Wait, we are not done yet. For our resultant vector, we also need directions because we have a vector. We need, for the direction, we can find this angle here, so I can say whether it is north of east or southwest, whatnot. To find this angle, I'm going to use tan theta and use my components that I found, that I have. 11 point, this is opposite, which is 11.48 dot 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 meters, no rounding, over my adjacent, which is 4.4 dot 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 in meters. So my angle is when I take the inverse tan of the quotient of these two numbers, and as a result, I'm going to get alpha y over alpha z. Take the inverse tan, and I get 68.66, which rounds up to 69 degrees, which means in my answer, I'm going to write at 69 degrees, then this is north of east, and north of east as shorthand because I'm running out of space. So here are the directions for the resultant vector, which is the total displacement of Leo in example 1. Now this is a very long example, and notice that this is very important. When we were doing number 3, which is adding the horizontal components and adding the vertical components, we were doing these independently of each other, which means I did not add my x components with my y components. They stayed separate in the addition process. Not until the end when we looked at triangles where that's when we put them together. Otherwise, the other important thing is when you are adding components together, you have to make sure you pay attention to the directions. If you get a negative number for the opposite direction, please remember to include the negative sign. Directions are important. These are your positive signs and negative signs. Please, please, please don't forget them. So what I'm going to do is I'm going to give you a chance to try the next problem on your own. And once you're ready, you're not sure how to tackle or approach it, try watching the next video, which is part 2 of 2.02 vector addition using components. But if you can do example 2, please try it by yourself. Otherwise, I will see you in the next part.